Optical imaging of brain function requires a model of how light propagates inside the skull. The model is used to connect light measurements taken from the scalp to changes in optical properties of the tissue. In turn, tissue optical properties and neural activity are coupled through hemodynamics. This effect is exploited in neuroimaging to construct tomographic maps of brain function. However, we can't measure tissue optical properties directly. The available data comprise a collection of light measurements from the scalp that are acquired over the duration of an experiment. The corresponding changes in optical properties must be reconstructed from these data. This requires an accurate model of how light propagates inside the skull. Construction of the light model accounts for a substantial portion of the NeuroDOT processing pipeline. The end result is called a regularized reconstruction. This is an algebraic expression relating light intensity measured from the surface of an object to changes in its internal optical properties. In this video, we derive the regularized reconstruction. We begin by introducing light modeling generally, then describe specializations that appear in NeuroDOT and that you will encounter in the hands-on tutorials. The presentation necessarily involves a large amount of technical material. Light modeling is a complex topic that intersects physics, differential equations, and numerical analysis. We will take up the mathematical details in a separate video series. The current treatment is conceptual, assuming only minimal background. The goal is to provide an intuitive understanding of the regularized reconstruction, what the terms mean, where they come from, and how they are used. To begin a discussion of light modeling, we consider how light from an external source propagates inside a medium. The two primary effects of interest are scattering and absorption. Scattering describes how light spreads from a focal point, and absorption describes how rapidly it attenuates. The effects are quantified by the scattering and absorption coefficients of the medium. These are formally defined in terms of photon behavior, but an intuitive understanding in terms of bulk light properties will suffice for our needs. Collectively, we refer to the two coefficients as the optical properties of the medium. In general, optical properties are a function of time and position, but for this discussion, we will assume the values are constants. In order to model propagation, light must be quantified. Here we use fluence rate, indicated by the Greek letter phi. Although it is formally defined in terms of photon flux, fluence rate can be understood as a measure of light intensity. In general, it is a function of both position and time. Light modeling can thus be described as determining the fluence rate resulting from one or more external light sources given the geometry and optical properties of the medium. A starting point presented in many treatments of optical imaging is the radiative transport equation. This provides a general model of light propagation based on arguments of energy transport. However, the RTE can be difficult or impossible to solve, especially for the types of problems confronted in neuroimaging. As a consequence, we work with a simplification called the diffusion approximation. This places some restrictions on the model, but generally provides acceptable accuracy. In addition, we introduce two assumptions that are used in many modeling packages, including NeuroDOT. First, we assume steady-state conditions. That is, we assume the fluence rate can vary from place to place in the medium, but not over time. This may seem counterintuitive since we seek to model optical properties that vary over the course of an experiment. Later, we'll bring in a trick to reintroduce time dependency into the model. Second, we'll ignore scattering. This is fundamentally a statement about the data. HDDOT acquisition falls into three broad categories: continuous wave, frequency-dependent, and time-dependent. Continuous wave is the most common sampling strategy currently used in optical imaging, and so we'll assume we are working with CW data in what follows. As such, we'll focus solely on changes in absorption, because continuous wave sampling does not provide information about scattering. Even with these simplifying assumptions, solving the diffusion equation analytically is generally possible only for simple geometries and source distributions. For real-world applications, such as modeling light diffusion inside the skull, we turn to numerical methods. Our tool of choice is the finite element method. Briefly, a mesh is defined that approximates the domain shape. The optical properties and source distributions are defined on the mesh, and the fluence rate is then obtained at the mesh node points by solving a system of algebraic equations. Although a relatively low-resolution mesh is shown here, the finite element model used in a regularized reconstruction typically contains hundreds or even thousands of nodes in order to obtain acceptable accuracy. An alternative numerical approach you may encounter in other resources is the Monte Carlo method. This builds the fluence rate distribution by simulating the propagation of individual photons in the medium. Monte Carlo involves fewer assumptions than the finite element method and offers greater accuracy in some types of problems. However, because finite element is faster and its accuracy is satisfactory for most neuroimaging applications, it is the numerical tool used in NeuroDOT. Finite element analysis can be applied to determine the fluence rate distribution generated by an arbitrary collection of external light sources. A useful special case is to calculate the fluence rate resulting from a unit light source applied at one boundary node. The fluence rate distribution in this case is called a Green's function, typically denoted using the capital letter G, and with the source indicated by the letter S and the node of interest indicated using the letter D, because often the node of interest will be at a detector. Alternately, a position vector R is sometimes drawn between the source-detector pair. Using the Green's function for a given point source, we can obtain the value of the fluence rate at any node in the mesh. We will refer to this as the illumination profile of the source. Additionally, it can be shown that the Green's function also describes the sampling profile of a detector. That is, it quantifies the contribution of each mesh node to the fluence rate that would be measured at a detector located at node D, given an arbitrary fluence rate applied across the mesh. By combining the illumination and sampling profiles, we obtain the most likely path light will take when traveling from a given source node to a given detector node. This is called the sensitivity profile of the source-detector pair, indicated here using the notation APK, where P is the measurement pair number and K is a mesh node number. Even though the sensitivity profile is technically non-zero at all mesh nodes, it's common practice to draw only the central lobe, indicating the region of strongest influence. This has the characteristic shape of a banana, giving rise to the term optical banana, which is often used instead of the term sensitivity profile. The optical banana is a handy visual aid for demonstrating how the regularized reconstruction is generated. Recall that we need to determine changes in tissue optical properties. Our data are pairs of source detector light measurements, and because we are assuming CW acquisition, only changes in absorption are relevant. Consider the effect on a given source detector pair measurement of a small change in absorption at a few node locations. Intuitively, we anticipate a stronger effect if the absorption changes intersect the optical banana for the source detector pair. Conversely, we anticipate a weaker or negligible change if they do not. Then, given a change in absorption affecting all mesh nodes, we can calculate its effect on any given source detector pair measurement by multiplying the change in absorption at each node by the value of the sensitivity profile at the node and summing the product across all nodes. We can carry out such a calculation for every source detector pair appearing in the model, that is, every source detector pair in the optode array used in the experiment. By arranging these calculations in matrix form, the result can be written as a vector of changes in source detector measurements calculated as the vector of absorption changes, multiplied by a matrix that encapsulates the source detector sensitivities. This matrix is called the sensitivity matrix. A graphical representation of the sensitivity matrix is included here at left. This is roughly formed by the union of the individual sensitivity profiles, although the details will depend on the geometry and optical properties of the model. We can write this expression more concisely by introducing the variable y for the source detector measurements, x for the absorption changes, and a for the sensitivity matrix. These are the quantities that appear in the regularized reconstruction. However, as formulated, the known and unknown quantities are reversed. We seek to determine changes in optical properties given light measurements, but this formula specifies changes in light measurements given changes in optical properties. What we have defined is the forward problem, referring to a class of problems in which model properties are given and are then applied to determine the model response. What we require is a solution of the inverse problem. This presents additional computational challenges. First, we cannot simply invert the sensitivity matrix and solve for the quantity of interest. The sensitivity matrix is not square. The number of rows in A is equal to the number of source detector pairs appearing in the model, and the number of columns is equal to the number of nodes in the finite element mesh. In a typical imaging application, the number of nodes will greatly exceed the number of measurement pairs. A way forward is provided by using a generalized inverse, also known as a Moore-Penrose or pseudo-inverse. This allows inversion of a non-square matrix in a least square sense, in effect fitting a solution to the data. However, a generalized inverse is not unique, and in most inverse problems, auxiliary conditions are imposed on the solution, usually enforcing a desired behavior of the model. This adjustment is called regularization. It is implemented by specifying one or more regularization parameters, here denoted by the Greek letter lambda. The idea is to obtain a sensible fit of the data when working with an underdetermined system, that is, a problem in which there are more unknowns than equations. We have now obtained a generic expression for the regularized reconstruction. This allows us to estimate changes in optical properties inside a medium given a collection of source detector light measurements on the surface. The key step is construction of a sensitivity matrix and the application of regularization to obtain a generalized inverse. Conceptually, the derivation is complete. Still, we will address 3 points regarding how the regularized reconstruction is implemented in NeuroDOT. Specifically, we'll present a few details about finite element modeling, describe how changes in light measurements are defined when working with optical array data, and, finally, describe the 2 specific regularizations that are used. A finite element model of the skull and brain necessarily includes multiple tissue types. These materials differ in optical properties. Baseline values as well as any physical constants required to construct the forward model are taken from the neuroimaging literature. Additionally, even though we depict a 2-dimensional mesh here for simplicity, bone, CSF, and gray matter comprise a layered 3-dimensional object. To generate a finite element mesh for such complex geometry, a sophisticated automatic meshing algorithm is used, applied to either a standard template or the subject's own anatomy if a structural scan is available. Typically, tetrahedral or hexahedral elements are used, and the model may contain on the order of 1 million nodes in order to obtain acceptable accuracy. This presents a non-trivial computational challenge, and NeuroDOT integrates efficient third-party software for fast finite element modeling. See the tutorials on NearFaster for more information. On a final note, the position of the array optodes must be specified relative to the finite element mesh. NeuroDOT provides tools for this operation that are described in a separate tutorial. So far, we've been imprecise as to how the changes in light measurements used in the regularized reconstruction are defined. As we shall see, the changes are assumed to be small and expressed as a ratio relative to a baseline. For this reason, the term differential change is used. The definition is motivated by the nature of data collection. In a typical investigation, the entire optode array is repeatedly sampled over the duration of the experiment. Consequently, the paired light measurements used in the regularized reconstruction do not vary continuously over time, but rather comprise a collection of snapshots. The fluence rate at a given location in the brain may change from sample to sample, but it is assumed it is constant within each frame. This assumption allows a baseline for each source detector pair to be simply defined as the average taken over all frames. The change in light measurement relative to this baseline is the quantity used in the reconstruction. The obvious approach would be to subtract the baseline from the measurement obtained in each frame. However, we instead use the log of the ratio. This is called the Rytov approximation, A justification of the Rytov approximation is beyond the scope of this introduction, save to say, use of a ratiometric difference gives good modeling results, assuming the change in light level in each frame is small. This assumption is satisfied in optical neuroimaging applications, with the change typically being less than a few %. What we now have is a regularized reconstruction that is repeatedly applied to each frame of data collected during the experiment. This allows us to compute differential changes in optical properties of the tissue in each frame, given differential source detector measurements from the surface. The sensitivity matrix and its inverse is only constructed once. What remains is to introduce the specific regularizations that are used. As noted previously, regularization is usually required to constrain the solution of an inverse problem. Two are implemented in NeuroDOT. First, Tikhonov regularization controls the spatial frequencies that appear in the reconstruction. This suppresses high-frequency patterns that likely reflect amplified noise rather than a true physiological signal. Second, spatially variant regularization is used to correct model bias due to oversampling of superficial tissue layers. Signal-to-noise decreases with increasing source detector separation distance. As a consequence, most of the usable array data comes from source detector pairs that are close together. This biases the reconstruction toward superficial tissue layers because light traveling to detectors close to a source remains near the surface. Spatially variant regularization is introduced to enforce a more uniform interrogation of the cortical depth. A full discussion of NeuroDOT regularization, including guidelines for identifying optimal parameter values, is included as part of the Reconstruction PowerPoint tutorial. This completes our derivation of the regularized reconstruction used in NeuroDOT. We apply this light model to convert paired measurements of light intensity recorded during an experiment into corresponding variations of absorbance inside the tissue. A final processing step allows us to estimate the responsible neural activity, expressed as a tomographic map of bold activation. The data is then available for statistical analysis or other post-processing. This video will have prepared you to work through any of the light modeling PowerPoint tutorials included with the NeuroDOT distribution. These hands-on exercises will allow you to apply the concepts presented here and generate a regularized reconstruction using a normalized structural template and sample data. A separate tutorial covers participant-specific head modeling, which can be performed if a structural scan of the subject is available. Additional information may be found in the resources listed here. Feel free to contact the development team with questions or post them in the comment section below. Thank you for your interest in NeuroDOT.